So this is from a lecture that I did at Black Hat in 2009. And so far, everything in this class has been discussing linkers and loaders that are supposed to exist. In this case, the question comes, like, if you have a firmware image for a device and you think that it's been tampered with, what would that look like? Specifically, I'm going to discuss how to add interrupt vector table proxy that allows you to hook individual interrupts within the microcontroller, and how to visualize that within a firmware image so that you can quickly compare two to see whether a foothold has been inserted. I'm also supposing that the attacker does not have access to the source code of the program that's being tampered with, so he'll be a bit lazy and the modifications will be minimal.
Could you, I'm sorry, but what type of interrupts are
Okay, so this is an MSP430, which from my lecture 2 days ago was the diagram on the far left. You have an interrupt vector table at the top of memory. You have flash memory growing down from there. And flash memory is where the code executes from. Lower down, you'll have RAM. This chip is capable of executing RAM, but the programming isn't stored there because that gets erased every time the chip is reset. Did that answer it?
Well, what type of interrupts?
Oh, so the interrupts are, there's 16 interrupts, each of which is 2 bytes long. So the interrupt vector table is 32 bytes total. Each interrupt is the address that the CPU will jump to when an event happens. The first of these that gets called is the reset vector, which is just the starting point at which code begins execution. So every time you pull the chip's reset pin low, and then it goes back high, on the rising edge, the program counter gets replaced with the reset vector. You also have one for the arrival of a byte on a serial port. This then tells, so in your program you would have a function that will receive a byte from the UART. And this function gets called every time the UART hardware receives a serial byte. You also have some for all of the I/O pins. So when you press a button on a keypad, that connects one pin to another. And this triggers an interrupt so that the handler function can then figure out which button was pressed.
Okay. And this is usually handled by the firmware and not the ROM? Or
Yes. The ROM only has a single interrupt, and that's the special ROM entry point, and that's not part of the table.
So when you say it has a special entry point, I hear it to be somewhat like the kernel syscall dispatcher entry. Everything that happens to this code happens through here.
It is similar to that, but for a different reason. In the ROM's case, adding this extra interrupt was a significant strain for the developers. So to prevent feature creep, they didn't allow the boot ROM to become too complicated. So everything that it does, it has to do without interrupts. Which is the other nifty thing to learn from this, which is that you don't necessarily need to have interrupts to do something useful. They make programming easier and they make your program smaller. But if you're patient and if you don't care about performance, you can poll for everything that you need. So the boot ROM actually implements its serial port in software instead of in hardware. And this gives you the dual advantages of not needing to use any of the any of the interrupts to receive the bytes. And it also allows you to use different pins than any legitimate UART on the device would use. So you don't have to worry about overlap. So the history of this was that in 2007, I wrote the first exploit for the MSP430. This is a packet that if you receive it, it will overflow the stack and then execute itself. 2008, I authored a reverse engineering kit for the MSP430. Don't use this now. IDA Pro supports the chip. And then in 2009, Mike Davis had announced that he'd written a smart grid worm. And he had a demo of this, but it looked like a lot of the details were going to get censored. So he never actually published any technical information about this. So this lecture was originally written to describe what I would look for in attempting to find a smart grid worm. So if I have 2 smart meters and I suspect that one of them has been infected, these are the signs that I would look for. Now, on this device, memory is very precious. Your maximum packet length is 128 bytes. You only have a few kilobytes of free RAM. And in flash ROM, a lot of the flash ROM will be taken up by the existing programming. So if you're trying to infect a meter without damaging it, you need to fit in whatever the slack space whatever slack space exists. And there's preciously little of that. There's also no real operating system. So you don't have system calls or function tables. You don't have symbols anywhere within the device. So on a Unix application, I can always find the printf function. If I ask the operating system for it, it'll give me a pointer to it. Here I don't have that ability because there's no operating system and there's no room for these symbols. Everything is statically linked. And also, all of the code is in flash memory, not in RAM. And flash memory has very different rules from RAM. The way that flash memory works is that when you erase it, you have to erase an entire page. You can't erase just a single byte. And erasing it makes every bit a 1. You can then clear selected bits. So if you have FFFF as a 16-bit word, I can turn that into any other 16-bit word I want. But if you have 0000, the only way that I can change that to anything else is to erase the entire page, which will destroy all of the data near it. So when you're making patches in a page that's partially used, you have to copy everything out, then erase it, then rewrite it, or only clear bits. And the code is running from, the legitimate system code always runs from flash directly. It's not copied into RAM. It's not loaded into RAM. The flash is part of the chip, can be fetched as quickly as RAM is fetched, and is run in place. This is another thing that you won't see on larger machines. Even in a modern PC, the BIOS image is in a serial flash ROM and is copied into RAM before it's executed. It's not executed in place as older PCs used to do. So the installation can be made reasonably hardware agnostic, by which I mean it can hit every chip in the family because all of the compilers for this family follow rules that allow the code to be efficiently ported. And portability doesn't come for free on an embedded system. If you're writing a Unix application and you write it in C, you know that it will compile for Mac OS as well as Linux. You will not be able to configure the display as easily as Linux, and you might have to run projection software that makes you hate freedom, but it will run. And things only become machine-specific when you start using inline assembly code or strange features that are unique to your operating system. Here, everything is specific to an individual hardware device at first. And if you want to make it work on different hardware, you need to either make it reconfigurable or you need to add software checks that figure out which features are available. You also need to reuse victim code wherever you possibly can. If the victim smart meter only has a kilobyte or 2 kilobytes of flash memory free, I won't have room for a wireless networking stack. But if I can hijack the stack that already exists in its memory, then I can use that to save space in my own program. And a kilobyte is not a lot. We're talking 5 or 6 pages of assembly code, 1 page of C code. And that's without any dependencies. You can also do a sort of, I forget what the memory security trade-off is. I had a point there. And the MSP430 itself is just 16 bits. So every pointer is 16 bits wide, and it's von Neumann, so it refers to the same thing all the time. There's no difference between data memory and program memory. It also has 2 different 20-bit variants in which code and data can exist in higher memory, but not all compilers support this. So if you're working on one of these chips, you might have a lot of memory above the 64 kilobyte line, which isn't used by the existing program and can be hijacked for your purposes. It also has a masked ROM bootloader, which I came up with a couple of exploits for, so they replaced it with a flash ROM bootloader. Where it's in masked ROM, it is perfectly identical for all of the chips of a given model, which means that you can reuse its communications functions to get a cheap serial port. Or you can look at one of the last addresses in it in order to learn the model number of the chip that you're using. Because none of this comes for free. If you've got a program that's running on an unknown machine and you need to know the model number, what do? Well, in this chip, you read the word that is at 0x0ff0, and that 16-bit word is the model number in hexadecimal. On the flash ROM variants, of course, though, this isn't reliable, and it might be erased for security reasons. Oh, pardon me? You made it. Okay. And the other thing is that I'm choosing this chip because I need a concrete example. If I did this for the AVR or the PIC or for MIPS or for Unix, the results would be different, and it's these differences that are the difference between being able to do something in theory and being able to do it in practice. So how do you find a function without linking tables? Yeah, I'm asking you.
I don't know. Wish I knew.
Reversing the firmware image beforehand and just getting an offset.
OK, so if you know the firmware image, then you can just put in the value and branch that as an absolute address, and that works. And if you don't quite know that, what's the next best thing?
Find a unique sequence of instructions.
Yes.
For example, if you just have it relinked, if the image just gets relinked or slightly recompiled for different
Yes.
submodels.
So in a lot of these devices, all of these standard functions will be perfectly identical, even through different revisions of the compiler, because the C library is sort of written once, half-assed, and then reshipped. I was reverse engineering one, and I actually found a bug in the absolute value function. It didn't cause a performance problem, but the assembler had misassembled one of the instructions to make it 4 bytes long instead of 2. So I wrote the compiler vendor, and I said, you have a bug in your absolute value function. It's 2 bytes longer than it needs to be. This is because of a bug in your assembler. On the MSP430, you have a constant generator. So if you're doing an immediate value, you can either specify that as a second word, or you can automatically specify 0, 1, 2, 4, 8, 16, and -1, because those are the values commonly used for masking. Their assembler wasn't doing this. So I wrote to the guy, and he wrote back saying, "Oh no, there's no problem. It's just a compiler thing. We'll take care of it." I looked into it further, and I wrote back saying, "No, the open source assembler that you ripped off fixed this bug in 2006. You should probably update your own code." And I never heard back from them. Now, radio drivers are a bit different because they're inlined. If you have a function that is only called once, anywhere. Could someone get me some water? If you have a function that's only called once, anywhere within the application, then there's no reason to make it a physically separate function.
Can you explain why 4 bytes long is a bug?
It's a bug because you might only have a kilobyte of code space. So if an instruction is twice as long as it needs to be, and you use that instruction several times, and every instruction that uses -1 as an immediate, like FFFF to mask, suffers from this bug. So this makes the code size a lot larger than it needs to be. This compiler vendor specifically brags that they have the most space-efficient compiler.
There's not a bug in it. It still works properly.
Right. Sorry, my throat's killing me. Oh. So the final part. Oh, thank God.
Cold water, hot water.
Why would you give me hot water?
Because you might want to adjust the temperature.
I remember when I was working in Taipei, and they had like the water cooler, and one of the engineers goes up to the water cooler, and it's got hot and cold. A little bit of hot, a little bit of cold, a little bit of hot, a little bit of cold. Sipped it to taste the temperature, and just did this to perfectly get lukewarm water as the combination. Okay, so then there are different tricks that you could do to hide this rootkit. But would you use them?
It depends if there's a way to remotely examine the memory of the machine. Because if you can't, this doesn't have any remote execution capabilities usually, so if no one can ever look at the firmware from somewhere else without taking apart the smart meter, there's no point in actually hiding it.
Right. And even if they could, there are like 12 of us who reverse engineer this platform worldwide. 3 of us do it well. So, and God, I hate Linux. So, yeah, a lot of times you don't actually need to hide it. So, to locate a function, you can use fingerprints. We're talking about locating it in general. So first you need to reverse engineer enough of the existing application in order to know where to change things. So for library functions, you can just look for exact duplicates, or exact duplicates with the addresses of child functions sort of masked away. So wherever there's a function call, you mask out the address that it's calling down to zeros. And then the same function will appear for the same compiler and a little bit of luck. The other trick that you can do, if you're trying to reverse engineer a small firmware image, this is by far the fastest way to do it. Look for ports. So on a PC application, you've got system calls and common library calls and shared library calls, and you can identify those things. Here we don't have them, but we still have I/O ports which are unique to the hardware. So the first thing that I do when I start reverse engineering a firmware image is I look for the function that writes a byte out to the serial port. And the way that that works in assembly language is that you have an I/O port, which is just exactly the same as a global variable that happens to have an address in the I/O region. You write to it as if it were RAM. And in the case of the serial port, it is, I think, 23 hex. So you just write a value into memory at address 0023, and that gets spat out the serial port. So if you're trying to identify the transmit byte function, that is exactly where you go. There will be exactly one function system-wide that writes to it, and anything that calls that function is performing a write.
But so if I want to hide a call like this, if it just behaves like a regular RAM address, I could do nasty things like use register indirect writes or something, and no one would ever find it, without looking really carefully.
Right. They can also run it in a simulator. Because this architecture is so simple, there are perfectly cycle-accurate simulators that you can run.
Okay. But they won't necessarily...
Well, then you can trap on it, because at that point it's just a Python program. But you're right that that would hide it on the first pass. In smart card firmware, you'll see all sorts of tricks like that. Or for machines that do not require aligned execution, like x86, you can have perfectly innocent machine code that does something perfectly innocent, malicious. And then the disassembler won't catch that until someone figures out that it's not actually executing from that address.
Take heed. This was a good topic for a course project.
The trickiest way to do it is you can use JavaScript to produce just-in-time compiled code that is innocent until you execute it 1 byte in. And then the code is already within the web browser's address space, and it's marked as executable. Ain't that nifty?
Okay, goes back to Netscape 3.
But that will not be portable because you can't depend on your JIT compiler compiling it just the way you want it.
Luckily, there are only so many operating systems, and we all run the latest version because we're scared to death of Flash vulnerabilities. I mean, whether you run this week's Firefox or Netscape 3, you know, damned if you do and damned if you don't. I'm gonna need like 3 more of these, if you don't mind. Just the cold. So when you have interrupt handling, I believe I've got a diagram of it. Yeah.
You're just hiding on 5 more.
I'll wait until he gets back to tell him that. Okay. This is a map of memory produced by MSP430 static. And this was produced by a very simple method, which is that every 16-bit word becomes 2 pixels. The addresses begin with 00 in the far left and all F's at the top right. The upper half of the address is the y-axis, and the lower half of the address is the x-axis. These regions down here are I/O space. And then I believe this is C00, and this region here is the bootloader ROM. Anything in blue is something that has a disassembled instruction that points at it. So these blue lines are global variables at the bottom of RAM. Above them, red with gray. Red is the color of potentially good disassembled code. Gray is the color of code that is not legitimate when disassembled. So the speckled gray region, this is RAM that's not used. So it's not erased. The white memory is erased. White represents all zeros, and then F represents all Fs. So unused RAM, which is cleared to 0, they tell me that I should have asked for 5. There you go. All right. So Black represents flash memory that has not been erased, or that has not been used. And white represents RAM that has been erased but has not yet been filled by anything. Then this gray and red represents RAM that either contains randomized values or contains values that happen to look a little bit like code, but because of the gray specks, we know that it's not really code. And you can see throughout this large region of the lower application, all of this is perfectly disassembled. The few specks of blue are where an instruction is pointing to something within it. And a few of those are false positives from the misdisassembled code here.
And how are you defining being pointed at?
If you are doing either a function call or you're writing to an immediate address. This region here consists of constants that are included in the application. Hence, you've got very well repeated patterns and some parts that involve lots of zeros. And then you can see blue pointers where this is being pointed to by different things. So these are the different sections of your application. You'll also note there's another program up here. And this green region at the very top, that's the interrupt table. Just beneath it and at the same offset, you've got a data structure in which everything but the very last entry is pointed to by something. So what is this? This is one program that sits at the real top of memory and proxies all of the legitimate system calls, which are up here, to their equivalents at the fake interrupt vector table down here, except for reset, which some idiot hard-coded. So in this device, the upper application runs, and then at some point later on, it cedes control over to the lower application. For everything that it cares about, it controls the immediate interrupt handler and is therefore able to hook it. And in hooking it, it can then change what happens when the function call is made. This is the simplest operating system you can have. This is taken from a commercial MSP430 debugger. So this is from the Texas Instruments JTAG debugger. The purpose of this code here is to act as a bootloader and to recover from a failed flash. So if you flash the device and something messes up, then on startup, because this program is run until the host computer tells it to jump to the other, it can use this program to replace that one. In my JTAG debugger, I've just realized that the program down here, the one in master-ROM, does the same damn thing. So there's no reason to have this at the top. But this is exactly how it would look if you made the cheapest rootkit. Because a rootkit sort of wedges itself between the program that's running and the hardware in the same way that an operating system wedges itself between the program that's running and the hardware. And in the same way that DOS boxes in Windows sort of believe that they're running DOS and that they're the only program on the computer, this lower program believes that it's the only program running on the microcontroller. It never has to know that there's something up here.
Could you point out what's ROM and RAM and flash?
I/O is at the very bottom.
Yeah.
Then it's just the first 2 or 4 lines.
Okay.
And then you have a lower image of RAM that this compiler is ignoring. Then you have this region here, which is the master ROM bootloader. Then you have RAM. And then from here all the way up to the top, you have flash. This chip has a lot more flash than RAM or ROM or the rest. And in this device, even though the ROM bootloader was present, and even though it still worked, it wasn't used.
What would happen if you try to write over that memory where the master ROM is?
So we actually wrote an exploit that depended upon this property. What happens if you try to write to a region that you're not allowed to on a PC?
You get a trap.
Right. Suppose you were cutting absolutely everything out of a PC that you didn't need. You're trying to design the hardware for a small microcontroller. Would you need such a trap?
No, so you just have to write fail or not do anything.
It's silently ignored. So recalling that the ROM is just beneath RAM and that the call stack grows downward, we wrote an exploit for the recursive factorial function. So the recursive factorial function just calls itself, and then that calls itself and calls itself. So it lets you get stack depth. And the stack depth is attacker controlled, but nothing else. The attacker can't actually put a value onto the stack other than what happens to be there for the, the descent. And the tail end of the stack will always look kind of similar, with the return addresses being the only difference. So what we did was, the call stack begins up here, and we grew all the way down into ROM, where writes are silently ignored. And then we let it return. So it writes its real return address over the ROM entry address in ROM. The write is silently ignored. And when it pops the value that it just pushed back off the stack, it returns back into our shellcode. The niftiest way that we did this was on AVR. Because on AVR, the RAM isn't executable, but we found a way that we could shove things into flash ROM, because it was being used as extra data storage space. So we've got our shellcode in code memory, but we don't have a way to run it other than this recursive factorial thing. So we run the recursive factorial way down to the bottom. Unfortunately, the AVR doesn't have a ROM. And it doesn't have code memory in the RAM either, so you can't overwrite code memory. But at the very bottom, you have I/O space. So we went all the way down to an I/O input port and then returned. And an input port, just like ROM, the writes are ignored. The read yanks the value back. Our remaining problem was that the value that it was yanking back for any digital input port would only be 8 bits, and the program counter is 16 bits. But the AVR has an analog input port. So we had a potentiometer wired into this chip. We were actually turning the potentiometer to control where within the address space we were going to land. Isn't that cool? So the interrupt vector table itself is just the list of interrupt handler addresses, and it's at the top of memory. So if you copy this to a lower address, and then for every target that you don't care about, you just immediately branch to the address in the lower table. And for anything that you do care about, you hook it. Then you've implemented the minimal operating system that proxies every interrupt that might happen and can silence them or do whatever other behavior it wants to do, while leaving everything else intact. The only difference in this will be a couple of clock cycles penalty on each interrupt that occurs.
But, for example, some nifty firmware that could compute the checksum of the entire address space would immediately detect this, because there is no way without writing a cycle simulator in the processor itself to protect
Yes.
some region of memory.
And there are people researching that, but so this is what the firmware looks like when it is proxied. This is what it looks like as just the output of the compiler for an application that is not proxied. And because this is the output of the compiler, the extra flash memory is just undefined. This is why when you recover an image from a real chip, the unused region is black instead of white, because it's FFFF instead of 0000. And the reason why is that when the chip is erased, it goes to ones, and it doesn't go to zeros unless it's told to. So all of your slack space remains black. You can also take this image apart and actually do a control flow graph of it, or a function call graph. When you have two applications, they stand out as two separate data structures. In these graphs, each vertex is a function, and each edge is a function call. With the interrupt vector table being out here, you'll note that, so on the right we've got the bootloader / rootkit, and on the left we've got the regular application. You'll note that the regular application has tons of functions, and they all call each other. The bootloader has to be kept lean, and in this case, it only cares about what happens at startup. So at startup, it asks if it should have any interaction with the host, and if the answer is no, then it just branches into the other program and forgets about it. This sort of star structure around the only circle on the graph, this is the interrupt vector table, and then each of these is just a branch to the interrupts as handled by the lower application. And this is also used without malice. So just finding one of these structures inside of an image does not immediately mean that there's a rootkit. It has another effect. You remember that I said that I came up with exploits for the bootloader. Well, one of them is that if you have one of these interrupt proxies, then the bootloader password becomes the password of the proxy instead of the password of the lower application. Because on this chip, when you connect to the bootloader, it will only allow you to read memory if you can give it a complete and accurate copy of the interrupt vector table. And they did that because they figured that it was the one thing that no compiler could screw up and make consistent. Because the interrupts of every application would have to be different. It's not true, but it turns out that it's true enough until you take into account that the incorrect bytes take longer to compare than the correct bytes, which allows you to time it out. So as far as the, before you can write this, you also have to get the code out, and the maintenance guys might be checking these devices. And you could imagine that the ROM bootloader would be used for that, because the ROM bootloader is the one that the maintenance tool would talk to, or a JTAG. Because you're moving the positions of all of the interrupts, you cannot make the bootloader password the same. And the entry sequences in hardware, so even though you're able to trap any interrupt that would go to the main application, nothing that you put in memory can supersede the bootloader, the ROM bootloader. The more modern flash bootloaders can be erased or rewritten or whatever else you want to do. It's also the case that the JTAG fuse in the chip can't be blown internally. And this also changed with later revisions. So if you're trying to infect a device and then sort of defend your code from being analyzed? Well, the bootloader password will be changed whether or not you want to change it on infection, because the bootloader password is the interrupt vector table. And you can't lie about it because you can't cause your code to be executed when the bootloader should be executed. As far as the JTAG fuse goes, if it's already blown, such as at the factory, then access is restricted without the password, and the maintenance guy is likely to erase your code before he ever gets a copy of it. If it's not blown, then any local attacker has access, even if it's the legitimate owner of the hardware attacking the rootkit. And you cannot blow it internally. So there's nothing in software that you can do to blow this fuse, which is inconvenient if you're trying to hide yourself. Also, it's also inconvenient if you're trying to secure a device in a firmware update, because if devices ship from the factory without the fuse blown, they can never be blown in the field.
How is the fuse blown then? Is there just some voltage applied to some external pin in a certain mode?
You apply 14 volts to the TDI pin after shifting it into the fuse blow state, which then sets a bit of EEPROM.
So you usually even can't fake the other hardware on your board to have it create that voltage, because no TTL chip will make that.
Right. Especially on that pin, because every other JTAG device, sometimes you have multiple JTAG devices connected to each other, and sometimes you have like a microcontroller that's in charge. But no other device ever wants high voltage on those pins. If they want high voltage, they will have a special pin for it. If you could find hardware that would be vulnerable to locally blowing its fuse, I would love to see that. For this chip. For other chips, it's very easy to locally blow it. The later MSP430s actually use flash memory for this. And on the, what's it called? On the Freescale chips, it's just the first 4 bytes of flash memory. But flash memory is a lot easier to fake out than EEPROM. So, so in the call graph, you have 2 disconnected graphs in which child connections are easy to find. So it's easy to tell that this function calls that other function. And it's easy to change which address is being called by masking bits down to zeros. So if I don't have enough room in my code to rewrite a page, so I don't have enough free RAM or I don't have enough time, I can still clear it. So if there's a function that's just, I mean, let's say in assembly we had a call to the function at address such and such. 4000 is a terrible example for this. So 4000 has a single bit set. So 4000 has a single bit that I can clear, which means that the only thing that I can convert the destination address into would be a call to address 0, which I really don't want. Unless I want it to, well, no, that would work, because that would cause a non-maskable interrupt if you try to execute from I/O space. And then the thing would reboot, and I control the reset vector, so I can trap that. You can also, I see what I'm saying here. The call from my code to a child function in the other code is easy to make, because you just type it in and you're done. Going backward is what's more difficult, because you have to do it while only clearing instructions or potentially causing traps. While the chip does not reset when an invalid address is read or written, it will reset if an invalid instruction is executed. So you can take an instruction and turn it into an instruction that is invalid by clearing a bit, and then that will give you control over where that goes.
So this is interesting. On the PC, you see unorthodox debugging implemented by writing an illegal instruction of as many bytes as you like. On x86, there are many choices, in order to create a breakpoint, which is not like your usual breakpoint. So dtrace actually uses it for some of its tracing. It writes an illegal, it replaces an instruction with an illegal instruction, and then catches the illegal instruction trap, which then becomes a breakpoint processor.
Yes.
But here you're saying that an illegal instruction is merely a reset that returns you back to what? To the bootloader entry?
Yes, the chip's default behavior is that if it thinks that it's in a damaged state, or if it thinks that the program has crashed, it jumps right back to the beginning. Now, normally, you have code there that will reset everything, but you don't have to have that there. You can have your own entry function. It's worth compiling just an empty main function in GCC and then disassembling it to see where it copies over the data regions and clears the zeroed regions and the rest of that. Yes.
Instead of messing with the flash, couldn't you also just use the timer interrupts that you have, because timers are usually linked to the cycle? So
Yes.
you can count out how, because microcontrollers are built to have really exact timing on their instructions. So you can have real-time properties that can count out how many cycles you'll need until you want to reach the instruction that you want to trap on. And you just load that into the timer.
The only tricky part there is in figuring out which timer to use, because you want one that's not reconfigured by the client code later. But that technique does work. And the weirder timers are very often unused. The other thing you can notice is that the calling conventions are compiler specific and unique to revisions of the compiler. So GCC uses register 15 for the first parameter, register 14 for the second, then 13, then 12. IAR uses the exact opposite order in its fourth revision. In its third revision, it was a 32-bit compiler grafted onto a 16-bit system. So the calling convention is that register 12 is the less significant 16 bits of a 32-bit word. 13 would be the other ones, but it's unused because you're only doing a 16-bit parameter. Then 14 becomes the lower half of the second parameter, with 15 being unused as the upper half. And you can, if you actually graph out which registers are used with what frequency, on IAR3, you see that 13 and 15 are almost completely unused. And each other compiler has its own convention. You can also identify compilers by looking for switch statements. There's any number of ways to implement a switch statement. You can add something to your program counter, or you can branch to an absolute address. You can also, like the move FFFF into register 15, this instruction can be assembled two different ways. So you can actually fingerprint the assembler as well as the compiler. And if you notice that a program is made which uses one compiler in some parts and a different compiler in other parts, it was probably written by two different people.
So that's how people do the Stuxnet attribution.
Yes. You can also recognize unused interrupts, because GCC will make them all run to a single function that sort of does nothing and makes the world OK and then returns, while all of the other compilers will leave it as FFFF. This is also useful if you want to hook something that's not used by anything else, because on the compilers that leave it as all Fs, well, you can clear individual bits, and because they're all set, you can then choose any address you like.
So the previous two slides really mean that there is no ABI.
No.
You can't hope to introduce another piece of code into the mix and have it play nicely, because if even the calling convention is different, then what can you do?
Well, the nice thing about standards is that there are plenty to choose from. And every time you think you'll fix this by making one greater standard to combine them all, well, you've just made the problem worse. So if you have an image that you think might have been modified, look to figure out whether it's one application or two, whether it's using one compiler or two, one assembler or two. You'll also note that interrupt vector tables usually have all of the interrupt functions in the same region. Here are two different interrupt vector tables. Which one of these has a rootkit and which one does not?
The left one, because most of the because this is being redirected to some other jump table somewhere.
Yes. And you can tell that how.
Because probably a jump instruction is 4 bytes long.
Uh-huh.
And it points to a table of instructions that is just always 4 bytes long. Which
Exactly.
A is not emitted by any compiler, and no one writes hand assembly anymore except hackers.
So, I mean, what he's saying is that on this one, you've got 403A used all over the place. And then these other ones have irregular distances between them. Whereas in this table, each one of these is 4 more than the one next to it. And a branch to an address requires 16 bits for the opcode and 16 bits for the address itself, which produces that 4-byte difference.
Yeah, 1x86 thing PLT.
A nice regular table of stubs that has entries of equal length. Same deal here. So I'm quite interested in knowing how else you would overload your interrupts. So usually overloading is a sign of something interesting going on, some really unorthodox either debugging or hijacking trick. I may a classic example of overloading a trap handler is swapping. When you fire a trap, and then you actually make up for it, saying, oh no, it's not a real trap. It's not a real seg fault. It's not a real unmapped address. It's the address that I actually know how to map, so let me do it and then proceed as before. The debugger, unorthodox debugging uses the same trick, and I hear that you can do the same tricks on microcontrollers, only more.
The one restriction that you have here that's the strangest, that you can get around through this proxying technique, is that the interrupt vector table is in Flash, not in RAM. So if you want the destination address to be reconfigurable, you have to bounce down to RAM and then from RAM back into Flash, which means that you have to set up like a trampoline of sorts.
Which we know exactly as the PLT-GOT combination. GOT is writable, PLT isn't.
Yes.
The same pattern repeats itself.
So a few conclusions on this is that microcontrollers are machines that are in many ways easier to understand than a PC. You can take apart a complete microcontroller application from the firmware itself and load it up in IDA Pro, and in a matter of hours, rather than in a matter of centuries, you can figure out what the purpose of every single byte within memory is. So malware for this platform is in many ways easier to write than for a PC. Everything is better documented. The memory is smaller. So you wind up with a case that it's easy to write, but almost no one is looking for it. These slides were pre-Stuxnet, by the way. So, I mean, prior to Stuxnet, it was almost a question as to whether or not anyone was bothering to attack these things. Because even though the vulnerabilities were certainly there, they weren't being made public, and exploits weren't bouncing around in the wild in a way that would like ruin your day. And I mean, these things are easy to write, therefore they're probably easy to recognize because you won't need to do anything to obscure them terribly well. And as a result of no one looking for them. So if you start looking for them and you manage to get a large enough set of firmware images, it's quite possible that you'll find one. To do this, you would probably need the help of someone who has a very large deployment of embedded systems, such as smart electric meter vendor. And the meters themselves are networked. Somewhere within the meter protocol, there's a peak function that allows you to dump out flash memory. You could potentially just ask the meter network to send you all of its firmware and then search through it.
What necessarily prevents the rootkit from actually sending out false information yet? Because that is just like...
Nothing prevents it except that the author probably assumes that no one is bothering to watch.
Also, the question is how much false information would you
be able to store?
Would you be able to prepackage? One of the most fascinating parts about rootkits is that there are rootkit engineering patterns. A rootkit is something that is not supposed to announce its presence by introducing random errors, which is where the Sony rootkit introduced for DRM purposes miserably failed because it made CD-ROMs not work. But that means, in fact, that you have to hug the original implementation of various system utilities very, very closely. And if you have to understand it very, very closely and borrow as much of it as possible. The same pressure is higher here.
So supposing that the read function were overridden or we didn't trust it. As I've shown here, it's very easy to trap the read function, make it point to your own code, and then replace the value that's read. But what's a lot more difficult, perhaps even impossible, to defend against is for the manufacturer to just take an unannounced ODE vulnerability and use that with a stack buffer overflow to fetch the meter firmware. Because to defend against that, the author of the rootkit would have to identify all of the cases in which the firmware might be exploited, and or modify his firmware so drastically that none of the existing exploits would work.
Which would in itself give it away. I mean, I have one defense against that for the rootkit to defend itself, which is that the rootkit just implements a simulator for the chip in itself that actually handles the I/O, and that runs an unmodified firmware image. That, of course, assumes that you have the space to store it, and that would also be my defense. That is that you fill up all the garbage and all the stuff that is unused in flash memory with completely guaranteed random data, wherever you get that from, and then read it back, because then you have no way of storing all that data and storing anything else. Because either you lose some of that random data you can no longer store, or you don't have the space for the code because you have 0 free bytes.
So there's been an academic trend of doing this in papers about calling it remote attestation. And there's a guy at Eurocom in France named Aurélien Francien who has made it his hobby to break academically proposed remote attestation techniques. And I mean, that you could come up with such and such a way that makes it difficult to remotely attest it, doesn't make for that interesting of a read. But where other people screw up in doing this makes for excellent reads. Aurélien, A-U-R, E with an acute accent, L-I-E-N, and then Francien, F-R-A-N-C-I-L-L-O-N.
And he's looking for grad students.
He is. He's,
I am a grad student.
I'm not letting you go.
well, yeah, if you're looking for a grad student position in the south of France, I mean, the weather is terrible. They've got, I lived there for a month and it was just awful. You know, I'd wake up in the morning and I'd say, I hate this place, and I'd walk over to the bus stop, and while I was waiting for the bus to come, I would pick oranges off of the trees that grew wild at every bus stop in the city, and I'd think, you know, I'm really suffering here. And the sun would always be shining, and, you know.
But they didn't have any good beer.
Yeah, I mean, the beer is almost as bad as in Germany.
Now it's out in public. Video.
I'm already on German national radio saying that, so. I mean, at least in France you can get Belgian beer.